Hi everyone, I'm Dr. Nitin Kumar Saxena, and in this my video lecture, I'll start to explain you the different specialized network theorems that can be used to solve the circuits. In previous lectures, we have seen that how can we solve the problems using Kirchoff's law, KPL and KCL. They are the most commonly used and versatile tool to solve any circuit. But what happens, like if we have some kind of specialized circuits, and specialized circuits we require some specialized theorems that can solve the circuits with less efforts. And for specialized circuits, we can go for some theorems that are Thevenin theorem, Norton theorem, superposition theorem, reciprocity theorem, and others also. So let us begin with the first theorem, Thevenin theorem. So according to Thevenin theorem, like if we have any kind of network circuit having sources, maybe dependent source, maybe independent source, maybe voltage source, maybe current source, maybe resistances, maybe inductances, maybe conductances, capacitances. But in starting, we will start with source, independent type, and the resistance as an element. So if we see any circuit, and in circuit normally we are applying any circuit to get any output voltage or any output current, so we can say that all the circuit can be confined together and we can take a single branch as a load from it. So if I'm saying, for example, a circuit is such like this. I'm again drawing a voltage source, one resistance, another voltage source, but one resistance, here another resistance, here one resistance, one more resistance, and finally I have one resistance over there. Suppose this is the circuit. Suppose this is a circuit having two voltage sources of 5 volt and 10 volt, and resistances like 5 ohm, 10 ohm, 15 ohm, 5, 10, 50, 10, 10, and 20. So total resistances in this circuit are 6 resistances. And if I am saying, okay, this whole circuit is confined with this circuit, this branch only. What does it mean? It means that the whole circuit we are considering as a part of the circuit which is connected with this 20 ohm. So in other words, we can say this 20 ohm is a terminal resistance, or in other words we can say this is a load terminal or load resistance. Load terminal or load resistance. We can choose any resistance as a load resistance. It's not necessary that you will take this resistance, outer resistance, as a load resistance. It's depends on the numerical, it depends on the question which is asked. You can take any resistance as a load resistance. You can this one as a load, this one as a load, this one as a load. Any resistance you can consider as a load. The procedure to solve the Thevenin theorem will remain same, that we will see later. So first, what is Thevenin theorem? And according to Thevenin theorem, the whole circuit which is connected with this load terminal can be represented as this simple circuit. The whole circuit, I'm again repeating, the whole circuit which is terminated at these two terminals or at this branch can be represented as this simple circuit, where this voltage source is called VTH, Thevenin voltage. This resistance is called RTH, Thevenin resistance, and this is the load resistance which is given over there in problem. So according to Thevenin theorem, any complicated circuit which is terminated across a load branch can be represented again, can be written again as a simple circuit like this, in which a voltage source and resistance is connected in series. This shows the whole voltage of the internal circuit or the circuit, which I am saying as an internal circuit, and resistance as a internal resistance. With this branch, load branch or load terminal or load resistance. Now the question comes that if we are changing this whole circuit with this simple circuit having VTH, RTH and RL in series, then we know the value of RL is 20. Now what will be the value of VTH and RTH? How can we find the VTH and RTH from this circuit? So you can say the VTH is the open circuit voltage across load. VTH is open circuit voltage across load, and RTH is the equivalent resistance of the circuit across load when voltage sources are short and current sources are open. Okay, so what I am saying that RTH is the equivalent resistance of the circuit across load when Vs is short and current sources are open. To understand these two things, let's again see this circuit where if I am considering this 20 ohm as a load, so what does it mean? Suppose I am saying this point as a A and this point as a B. So naturally this AB is a branch having the load. So this is a load branch and the value of the load resistance is RL equals to 20. That I have already written here. Now you see the first point, how can we find the value of VTH? To find the value of VTH, what we will do? Open circuit voltage across load. So when we open this branch and the voltage across this point A and B for this circuit is called open circuit voltage across load and given by VTH, right? So if we solve this whole circuit, then we can find the value of VTH, and this VTH will be the value given in this figure, right? Similarly, RTH is equivalent resistance across load. So RTH will be, this will be RTH. RTH will be the equivalent resistance across load, right? When voltage source are short and current source are open. So if you see the circuit, in this circuit we have one voltage source here, one voltage source here. We don't have any current source. So what we will do? We simply short this and simply short this, and this is simple circuit having the resistances connected in this way. So if we solve it, we can find the overall resistance at terminal RTH. Is it fine? So you see, in this way, if we know the value of RTH and RL, if we know the value of For this circuit, again I am drawing VTH, RTH, RL. So this is called equivalent Thevenin circuit. Equivalent Thevenin circuit. Right? And if I am saying the current IL is flowing in the load, so what will be the value of IL? IL will be total voltage VTH upon total resistance RTH plus RL. So this is the final expression for Thevenin theorem, that from Thevenin theorem, if we find the value of the VTH and RTH, then the current flowing in the load can be calculated by this formula. IL equals to VTH divided by RTH plus RL. So I hope the theoretically Thevenin theorem is clear for all of you. Now let us see one example and try to solve the example with the help of Thevenin theorem. Okay, suppose this is a circuit. Again I am drawing and I am saying in this circuit, this load is connected across branch AB and the value of the load is 20 ohm. Okay, so if this is a load of 20 ohm which is connected for this circuit, 20 volt voltage source, 10 volt voltage source, 15 ohm resistance, 10 ohm resistance, 5 ohm resistance. So now I want to apply the Thevenin theorem and want to know what will be the load current for this circuit using Thevenin theorem. So let us start with first point. What is the first point? Step 1, to find the value of VTH. So step 1, find VTH. So for getting the value of VTH, first we will draw a equivalent circuit from this circuit for getting the value of VTH. So what will be the circuit? As we know from the theory that if we want to draw a circuit for VTH, so this will be the equivalent circuit for getting the value of VTH. The load terminal will open and whatever the voltage will come at this point, that will be known as VTH, right? So we will start similarly that we have studied with Kirchoff's law, and simply we will try to find the value of the current first in the circuit. Suppose I am saying again a current I is flowing here. So when I is flowing here, so in 10 ohm the same current I will go. At this point what will happen? There is two branches, the branch this one and the branch this one. So according to KCL the current should be divided, but if you seize it, then this circuit is open. If you will flow the current in this circuit, there is no path to go forward. Okay, so in short, we can say that if the circuit is open, there will be no possibility of the flow of current, and hence the current will not go in this direction because it is already open. And hence, what will happen is all the current will come from this point to this point, and hence the current in this branch will be I, right? Again, the same concept at this point, what will happen? The current I is coming, but since this is open, so no current will go there, and hence all the currents will come this side I. So I is coming here, again I is coming here. So again, our point is okay because whatever the current is going out, the same current is coming in. So our KCL is valid here. So it's following the law. This step 2, which I have told you in Kirchoff, is also valid here. So for this circuit, now you put the polarities. So this is positive, this is negative, this is positive, this is negative, this is positive, this is negative, and we have only one loop. So for this loop, if I draw, I'll write the Kirchoff's voltage law. Suppose I'm starting from this point, I'm going this like this and this and this. So from this point, I'll go to this point. What I get? Minus 20. What I get? Minus 20. Right? Now from this point to this point, plus 10i. Now from this point to this point, plus 10, because plus 2 minus we are moving. Here plus 2 minus again, so plus, and the value of voltage 5i. Now here to here, plus 15i equals to 0. Solve this. Minus 10 plus 5, 15, 20, 10, 30i equals to 0. So I is 1 upon 3. The value of the current is I is 1 upon 3 ampere. Is it fine? Right? Now, after getting the value of I, now what do you want to know? The voltage between A and B. You can write the voltage between A and B will be VA minus VB, which we will call later on VTH. Right. So for this, you start writing KVL from the point A and move like this. So when we start from the point A, so we can write like this: VA at this point plus 10 plus 5i, come to this point B. Why I am writing like this? You understand this? Suppose what I am here supposing, I am supposing like this, that I am supposing like this. There is one voltage source like this, okay, and the value of this voltage source is VA minus VB or VTH. So I am taking this as a positive point, this as a negative point. So I am writing VA as a positive, VA as a negative. So what I am doing now, I am starting from the point A and moving till point B. So when you are going to get the value of VTH, what you will do, you will start from point A and will move till point B, so that you can get the value of BA minus BB. And this is up to you whether you take this part or this part. We have two different paths. So it is totally depend on your choice whether you go for this one or whether you go for this one. Okay, the answer will remain same. Okay, you can check it also. So when we move like this, so we are moving from VA. At this point we are moving from plus to minus, so plus 10. Here plus 2 minus, so plus 5i minus BB equals to 0. Right, now find the value of VA minus BB. This will be minus 10 minus 5i equals to minus 10 minus 5 upon 3. Right, again solve this to minus 35 upon 3 volt. So you see the value of VA minus VV is VTH. And here we are not bothering about the sign, whether the VA minus VV is positive or negative. So in short, if we are taking only the magnitude, so we can say that the value of VTH, comes 35 upon 3 volt. Right? So the first point is over. In first point, we have to find the value of VTH. How can we find the value of VTH? Simply by opening this terminal, we can find the value of VTH. How? You open, now you apply KVL, find the current in the whole circuit. When you know the value of the current, you start from point A, move like this and go to the point B. And this value of VA minus VV will be the value of VTH. And doesn't matter whether it comes positive or it comes negative. Fine. So the first point is over. Now let us move to the second point. What is the second point? The second point is to find RTH. The second point is find RTH. So for getting the RTH, the concept is open the load terminal, open the load branch and apply that if voltage source is available, short it, and if current source is available, open it, and for the equivalent circuit, find the value of resistance across the load branch. So what you can do for this circuit, if you write the equivalent circuit, if you draw an equivalent circuit for RTH, what you will do? Simply, this is a voltage source, so short 10 ohm, 15 ohm, voltage source again short, and resistance 5 ohm, and here RTH between the point A and B. The value 5, 10, 15. Now you see, now you want to know the value of RTH here. You see, to find the value of RTH, what you will see here, when you start from this point, you see 15 ohm and 10 ohm, the same current flow here. And since same current will flow here, suppose I am saying current I is coming from here. So I will go like this, I will go like this, I will go like this. So what does it mean? This means 10 ohm and 15 ohm current is common, and common current means these resistances are in series. So what we will say, 10 and 15 ohm are in series. And for series, you know what we will do? We will simply add. So 10 plus 15 will be 25. Okay, so what we can do next step? Next step, we can make a single resistance in place of this two resistance, 10 and 15. So the value will be like this, 25 and 5. Right? Now you see, if I am again assuming the current I is flowing like this, so this current will distribute among these two resistance, 25 and 5. The current is distributing while the voltage across this and voltage across this is same. If current is distributing and voltage is same, this means these two resistances are in parallel. So 25 and 5 are in parallel. So what is the value of this equivalent? 1 upon 25 plus 1 upon 5. This will be 1. Suppose R, I am saying, solve this, plus 5, so 6 upon 25. So R is 25 upon 6 ohm. So this means if I remove these two, so I can write this resistance, value of this resistance is 25 upon 6 ohm. And you see, this is the value of RTH. Okay, so RTH is what? 25 upon 6. So right here, RTH is 25 upon 6 ohm. Is it okay? So we have calculated the value of VTH. This is 35 upon 3. RTH, this is 25 upon 6. So I know the value of VTH, I know the value of RTH. So I can, third step, I can draw an equivalent Thevenin circuit. So step 3, equivalent Thevenin circuit. So equivalent Thevenin circuit is RL is 20 ohm, RTH is 35 upon 3 ohm, volt, RTH is 25 upon 6 ohm, VTH is 35 upon 3 volt. This is okay. So equivalent Thevenin circuit shows the circuit and the value of RL is 20 ohm, the value of RTH is 25 upon 6 ohm, and the value of Thevenin voltage VTH is 35 upon 3 volt. So the question was, find the load current using Thevenin's theorem. So the load current IL, the formula we know, VTH upon RTH plus RL. Now substitute, when you will substitute RTH, 35 upon 3 divided by 25 upon 6 plus 20. Solve this, 35 upon 3. So 25 plus 120 upon 6. So when you solve this, 35 upon 3 divided by 145 upon 6. So next step, 35 upon 3 multiplied with 6 upon 145. Why I am doing so? Because students, I saw many students who was so much confused when they do the calculations for such type of circuit, and they make many times they make mistakes in getting the accurate result. So if they are getting any confusion, they can do like this. So 3 2s are 6, 5 29, 5 7. So the answer is 14 upon 29 ampere. If you want in decimals, so you can do solve by using calculator, and you can get it in decimals also. So I hope you understood how can we find a load current using Thevenin theorem. So next class we will try to solve the circuit using Norton theorem, and we will see that what is the relation between Thevenin theorem and Norton theorem. Thank you very much.